Good afternoon, everybody. My name is Cong. I'm glad to show our work named vTurbo. This work is done by me, Sahan Gamage, Purdue, Professor Ramana, Kompella, and Professor Dongyan. Cloud computing is one of the most transformed trends in recent years. Many enterprises are increasingly migrating their job to some public cloud, like the Amazon EC2 or Microsoft Azure. By pursuing or leading the cloud servers, with the pay-as-you-go charging model, they benefit a lot from saving money in running applications. One key feature influencing the cloud cost is server consolidation, hosting multiple VMs in one server. In order to pack more VMs in the single physical machine, the CPU sharing among VMs is quite common. It means once a VM is ready for execution, it may not find a free physical CPU immediately. Thus, it has to wait for its turn, causing the CPU access delay. When VMs run some IO-intensive applications like the web server, NFS, database, or memcached, the CPU access delay may translate into the IO processing delay. We observed that the IO processing delay caused by the CPU sharing can negatively impact on the I/O performance of both the network and disk I/O. To explain this more closely, let's look at the I/O processing in some modern OS. When the I/O interrupt reaches the CPU, typically there will be two basic stages involved in the I/O processing. First, the device interrupts will be synchronously processed by the IRQ context in the kernel. All data is buffered in the kernel buffers. Then, the applications may eventually copy all data from the kernel buffer to its user-level buffer in an asynchronous fashion. If the OS is directly running on a physical machine, the I/O processing delay is negligible. However, if the OS is running on a VM sharing the same core with other VMs, the IRQ processing can be delayed significantly because the VM may not be running when the I/O event occurs. Let's see some examples. Notice that the time bar in this picture is vertical. So in the virtualized system, there will be a buffer between the hypervisor and the guest OS named shared buffer. All packets received by the hypervisor will be first buffered in this buffer when the target VM is not running. When the target VM gets scheduled, all data will be copied from the shared buffer to the guest OS. In case of the TCP, all coming packets will be staged in the shared buffer, and the synchronous I/O processing may not happen due to the VM scheduling, especially when the target VM is not running. So this may delay the X generation, delay the whole I/O processing, and degrade the TCP throughput. This picture is similar to the previous one, but we will show some detail in the shared buffer between the hypervisor and the guest OS, the application buffer in the guest OS. For UDP flows, there's no such a time-sensitive X generation which governs the throughput. So the UDP client will continue sending data to the server without receiving any request and any response when the target VM is not running. But the size of the shared buffer is limited. So when the shared buffer is full, the coming packets will be dropped by the hypervisor. When the target VM gets scheduled, only the buffered packets will be copied from the kernel shared buffer to the target VM. In this case, only 2 packets instead of 4 will be copied to the target VM, which is less than the received packets by the hypervisor, resulting in the UDP throughput degradation. IRQ processing delay also affects the disk I/O. The application usually just write to the kernel memory and return. When the kernel memory is full or reaches a certain threshold, the IRQ context handling the disk I/O will flash all data in the memory to the disk in the background. So when the target VM is not running, the IRQ context cannot keep flushing data in the memory to the disk until the target VM gets scheduled again. So there's a gap during the data flushing. Now we have known the main problem is the IRQ processing delay caused by the CPU sharing. In order to reduce this delay, one intuitive method is to uniformly reduce the time slice of all VMs running in the system to make each VM get scheduled sooner. This method works well for those I/O-intensive applications. The smaller time slice leads to higher throughput, but it's horrible for those CPU or memory-intensive applications. So this method cannot benefit both the I/O and the CPU-intensive applications. In order to solve this dilemma, we propose a new solution named vTurbo. Our idea is very simple. We try to offload the IRQ processing to a turbo-sliced dedicated core named the Turbo core. The Turbo core, in fact, is just a regular CPU. The only difference is that we set an extremely small VM scheduling time slice on this core. The other cores in the system are called regular cores. We only run the general application on the regular cores. To achieve this goal, we gave each VM one additional virtual CPU named the Turbo CPU, Turbo V CPU, which only run on the Turbo cores. And the other virtual CPU called the regular V CPU can only run on the regular cores. And we ping the IRQ context to the Turbo V CPU. With this method, we can significantly improve the I/O throughput of TCP, UDP, and disk I/O. Another advantage of our solution is that it enables a self-adaptive system. Because the guest OS knows the workload running inside, it can determine whether to use the Turbo core or not by itself. Many existing solutions require classify the VMs into CPU-intensive or I/O-intensive VMs in advance. But such a classification is not easy in the real world because most workload in the cloud is mixed and unpredictable. Now let's see the design of vTurbo. If we only had the regular cores, the VMs running on the regular cores will be scheduled in a round-robin fashion, causing the long CPU access delay. Now we have the Turbo cores run simultaneously with the regular cores. Because the VM scheduling time slice on Turbo cores is very small, the Turbo V CPU running on the Turbo cores can get scheduled very, very frequently. So the CPU access delay on the Turbo core is very small. We can assume they just run on the physical machine. So the IRQ context can process the coming packets in a more timely fashion and buffer all packets in the kernel buffer. When the regular vCPU holding the application gets scheduled, the application will eventually copy all data from the kernel buffer to its user load buffer. Since the IRQ processing delay is shrinks a lot, we can process more I/O events in the same time and get higher I/O throughput. Let's still see the three examples with vTurbo. First, disk write. The application still writes to memory and return. When the memory buffer in the kernel is full or reaches a certain threshold, the IRQ context running on the Turbo cores will keep flushing the data in the memory to the disk, no matter the regular CPU holding the application is running or not. So this time, there's no gap during the data flushing. This is a UDP scenario. For UDP, the vTurbo will still process the coming packets more timely and put the packets in the kernel buffer. So the default size of kernel buffer in Linux is not enough. We need to increase the kernel buffer size to a larger value to hold all packets received when the target VM is not running. So this time, with the increased kernel buffer and the vTurbo, we don't need to worry about the limited size of shared buffer between the hypervisor and the guest OS, because it will be drained frequently by vTurbo. All packets will be moved to the kernel buffer. When the regular vCPU holding the application gets scheduled, all data will be copied from the kernel buffer to its user load buffer. We can improve the UDP throughput simply by offloading the IRQ context, improving the kernel buffer, but that's not enough for TCP. This is the interesting thing. For TCP, when the TCP server process calls the receive system call, it will lock the socket. So all coming packets can only be buffered in the backlog queue instead of the locked receive queue. And the default TCP stack will not generate ACK for the packets in the backlog queue. And it has high probability when the regular CPU holding the application is not running, the application is still holding the lock. So even though we have the vTurbo, can process the coming packets and put it in the backlog queue, since there's no ACK generation, the TCP, when the congestion window on the TCP client is full, the TCP client will stop sending data to the server. So the IRQ processing, the I/O processing delay still exists. To solve this problem, besides offloading the IRQ context, increasing the kernel buffer, we need to also modify the TCP stack to generate ACK for the packets buffered in the backlog queue. This time, with a vTurbo and timely ACK generation, the TCP flow between the client and server will be maintained. When the regular vCPU holding the application gets scheduled in the next round, all data in the backlog queue will be moved to the receive queue and then copied to the application level buffer. Now, it's clear that vTurbo can benefit a lot for the I/O-intensive VMs. You may ask, is that fair for those CPU-intensive VMs? Shall we give more CPU resource to those I/O-intensive VMs? No. We still try to guarantee the overall fairness among all VMs, because the turbo cores are not free. In order to keep the overall fair share, we will calculate the credits on both the regular cores and the turbo cores. In order to boost the I/O performance, we will guarantee the CPU allocation on the turbo cores first. If the total CPU allocation of a VM beyond the fair share due to using the turbo cores, we will deduct its credits on the regular cores and give the allocation and give the deduction to the VMs which don't use the turbo cores. The detail of the scheduling is in our paper, so due to time limit, I will not show them here. In order to evaluate our solution, we implemented a simple prototype based on the ZenVMM. We need to modify the VM scheduler in the hypervisor, modify the TCP stack in the guest OS. Note that the packets in the backlog queue are not always in order. To simplify our implementation, we only act the in-order packets in the backlog queue. This is the setup of our evaluation. We use the ZenVMM we use is Zen 4.1. We run Linux 3.2 in both the driver domain and the guest OS. In each experiment, we only expose one core as the turbo core, and we try to simulate the mixed workload in each VM. First, let's see the evaluation of the disk. We run the I/O zone benchmark in the VM sharing the same code with other 3 VMs. We vary the record size from 1 megabyte to 16 megabytes. For any size record size, we can significantly improve the disk write. But for the disk read, we get less improvement. This is because even though the vTurbo can get data from the disk to the memory, the regular vCPU holding the application is not running. The application cannot make further read request until it gets scheduled again. This is the results for the network evaluation in the 1 GB network. For the UDP scenario, we can almost get the full network bandwidth because there's almost no packets dropped by the hypervisor. For the TCP flow, we still can get amazing results. But since we only act the in-order packets in the backlog queue, once a packet was lost during the transfer, the vTurbo in the TCP stack will stop working. So we didn't get the line speed this time. Since many data centers and the cloud are upgraded to the 10 GB network, so we also repeat our experiments in the 10 GB network. This time, we also significantly improved both UDP and TCP throughput. Because in the 10 GB network, the regular CPU will be very, very busy. For the CPU sharing scenario, the application may not get enough CPU cycle to copy the data from the kernel buffer to its user buffer. So this time, we didn't get the line speed either. We also tried some application-level benchmark, for example, NFS. We run the NFS server in the VM sharing the same core with other 3 VMs, and export one directory of this VM, and run the I/O zone benchmark in another physical machine, which mounted the exported directory. No doubt, we can significantly improve the disk write, because we have already shown the benefit of vTurbo for the disk write and the TCP. To our surprise, we also get the amazing result for the sequential read. Recall that we didn't get a significant result for the disk read in the micro benchmark. After some after analyzing the job, the task, we figured out the reasons. Because the latest version NFS utilizes the prefetching for those sequential read operations. So this time, the NFS server can accept a bunch of read requests each time. And the application process will be able to process many, many read requests when the regular vCPU is running, and delegate the actual file read to the IRQ contact running on the vTurbo, thereby achieving a much higher throughput. We also try some more complex system like the patch audio. We run 3 audio components in 3 VMs running in 3 different physical machines. Each audio VM shares the same core with other 3 VMs. This table shows some basic operations done by the audio. With vTurbo, we can improve the throughput of audio almost 40%. Since each turbo core can be accessed by multiple I/O-intensive VMs, in order to show vTurbo does support multiple I/O-intensive VMs running simultaneously, we run 2 instances Apache Audio simultaneously. This time, in each physical machine, we run 2 Audio VM, sharing the same core with other 2 VMs. Then, we got a similar improvement in each instance. These are some related work to vTurbo. First, vSnoop and vFlood also try to offload the TCP function from the VM to the driver domain, but they only work for the small size TCP flow. Well, vTurbo works almost for any size, any I/O. vSlicer is a low latency VM scheduler. It can shrink the VM scheduling delay to a certain value, but this value is not small enough to significantly improve the I/O throughput in data center or LAN. vBalance try to forward the I/O interrupt to the running virtual CPU of a virtual SMP VM, so it only works for the virtual SMP VM. Even for the virtual SMP VM, we cannot guarantee the IRQ processing and the application are running on the same virtual CPU. If they are running on 2 different virtual CPU, we cannot guarantee the 2 virtual CPU get scheduled simultaneously either. So even for the virtual SMP VM, vBalance cannot get the line speed. The last work is presented earlier in this session. So this work also tried to improve the I/O performance of VM. This work focuses on reducing the overhead of device interrupts, and they assume there's no CPU sharing. In their evaluation, they gave each VM one dedicated core to run the application. Well, our solution tried to improve the I/O throughput of those VMs sharing the same core. And we focus on reducing the overhead of VM scheduling delay caused by the CPU sharing. Finally, let's conclude our solution. We try to improve the I/O throughput of the VMs sharing the same core with other VMs. Our key idea is that we offload the IRQ processing to a turbo-sliced dedicated core. Our results show that we can improve the UDP throughput up to 4 times, the TCP throughput up to 3 times, and the disk I/O up to 2 times. We can also benefit for some application-level benchmark. For example, we can improve the NFS throughput up to 3 times, improve the audio throughput by up to 38%. Thanks for your attention. If you have any questions.
Wenji from Fermilab. I have a question. If in your slide you said you improved the TCP throughput 3 times, but the TCP throughput is finally decided by how finally data be consumed by application. If your application and your VM is not scheduled, is not running, and how you can improve the 3 times of the throughput?
Here, we just improve the I/O throughput of the TCP receive. So when the TCP server is not running on the regular CPU, the IRQ context running on the vTurbo can process the I/O event and put the received packets to the kernel buffer and generate the ACK for these packets. So since the IRQ processing on the turbo core will run frequently, so we can process the coming packets in a very timely fashion. When the application running on the regular core gets scheduled after several or 40 or 50 milliseconds, it will eventually copy all data from the kernel buffer to its user level buffer. Even though the application running on the regular core is not running, we still keep the whole I/O processing, partial I/O processing in the kernel ongoing. So the TCP flow between the client and server will be maintained, even though the application is not running.
But still, the application consume the data. If the application cannot consume the data, your TCP buffer is finally be filled, and you cannot send out the X.
Sure. So if the application need to process the data and give a response, that's not a scenario we want to work for. But I have said, we have another work named the vSlicer, which is a low latency scheduler, can shrink the VM scheduling, so can shrink the delay of the application. In fact, we plan to combine the two work together. In future, we can provide the low latency on the application and the high throughput.
Okay, we can talk about it later.
Okay, thank you.
Hi, Tim Wood from George Washington.
Hi.
I have 2 questions. So one is with this micro time slice that you have for your turbo cores, I presume there's a lot of overhead just for this context switching back and forth. So is that much of a bottleneck? Do you think optimizing that would improve your results in a significant way?
Okay. First, if there are a lot of I/O in the system, the kernel will be interrupted anyway because there are a lot of I/O. What we did is not big different from the physical machine. Second, because we only run the IRQ processing on the turbo core, we run the other application, for example, the CPU-bound application on regular cores. Those CPU application will not be interrupted by the I/O interrupt. So we also have some, if you need, we also have some result for the cache misread on the turbo core. It's not significant.
And my other question was, how does this scale up as you have more and more VMs on your system? Do you just need to dedicate a few more of these turbo cores that you divide up?
I think it depends on the workload. If there are a lot of I/O workload, one turbo core is not enough. You need more I/O turbo cores, maybe 2 or 3. It depends on the workload. So for our implementation, we have shown we can support one turbo core. We can support 3, 4, 5 simultaneously running I/O intensive VMs.
And was that? I mean, after 5, is it hitting full capacity, or is that just as far as you?
Sorry.
At 5 VMs, were you hitting sort of maximum capacity on your turbo core, or do you
No,
think it,
even for 5
so you
VMs,
might be able to support more?
we still have enough CPU resource on turbo core.
Okay, let's thank the speaker.